Fortunately, the math has not changed,
Yeah.
to my knowledge. All right, questions up to here? All right, so come up with our prediction. I did this once years ago, and we were only 40% off, so here's hoping. All right, so the length here, this length here is actually not the same as this length here. So let's just, I probably should do two different subscripts there.
Oh, man.
This is the vibrating length, so I'm going to put a little v there for L sub v. And this is the length of the string for which we're finding the mass. So I'm going to call that the full length, L sub f. Because if I just found the mass of this piece right here, I'm ignoring the mass of the string there and so forth. And possibly I might take a bit of string that small, but it is preferably, even though I don't want 3 meters of string here, I want probably 3 meters of string to find the mass of it. And I have already done this. And so it's a matter of, can I find it?
I have a question, but I don't know if it's
Yes.
related exactly. If you were to take all the mass off of that string, what would happen to it when it was vibrating? Would it just kind of go everywhere?
Yeah, and there's a good chance that the string would just come out from
Okay.
that side of it.
Okay.
We are working on the assumption that the string is massless as far as the tension is concerned. We assume that the string has so little mass that it's insignificant compared to this, but as we put less and less mass on here, the mass of the string starts to have more of an impact.
Okay.
Sorry, those lengths are the vibrating length.
The vibrating length is the length from the string vibrator to the top of the pulley.
I'm sorry, the equations about the word.
The vibrating length is what we'll be using to determine the wavelength of the wave. The full length is the one that we'll be using for determining the string density, the linear density.
Oh, so that's just the entire length, and then that's just the length of one of the waves.
That LV is just the length of this. The full length would be from tip to tip.
Oh, okay. That sounded awesome.
That's not a little bit worse.
What they get for forcing students to do labs.
All right, so I had, hold on. Okay. I took a piece of string that was 3.0485 meters long. So my full length is an L. 3.048, is that what I said?
3.0485.
045, thank you. Meters long. I found the mass of that, and the mass of that was 3.16 grams. And the offset for the balance,
Oh, we're gonna do, oh no.
I had it actually 0.00.
Okay,
I made sure I had it lined up.
so there's no like, we don't gotta do like, what was that even called? I forget.
Certainties.
Yeah,
Uncertainties.
uncertainties.
Okay.
Sorry, I missed that. What was that?
You don't have to do it, no.
Yeah, never mind.
Okay. Sometimes my bad hearing. Oh, by the way, in the class from, I guess it was Monday's class. And I started recording at the break, and some of you were talking about the class.
Uh-oh.
And, you know, what, nothing was said that I took offense at, don't worry about that. But the comment that I think the first two labs were so incredibly hard, and I think an 8-week class, yeah, I need to cut back on that one. That was, I agree with you, and it won't help you at all, it'll help the next group, but perhaps they will sing songs.
So yeah, we could get our pictures taken and lined up.
Yeah.
Yeah.
As the
founding
martyrs.
Founding fathers of physics.
All right, so the linear density here, well, actually, we can just plug that in. This is L sub F. Plug it into there, so we can find the linear density, or we could just plug the number straight in the way I've set up the formula. The tension is based upon the weight of this, and trusting this for some unknown reason, I had 20, 100, and a 50, I think. 50. So I have 170 grams sitting on the end of the string. So basically I got a string here, I got 170 grams. What's the tension in the string? Or how would you find the tension in the string?
Why is it not just 170 grams?
Why is it just not 170 grams?
Yeah.
Because 170 grams is mass and tension is a force.
It's the acceleration due to gravity times the mass, right?
Yeah. If this is in static equilibrium, that means that acceleration is 0, which means that the total force acting on the hanging mass is 0, which means the force up, the tension, is equal to the weight down. So if we just find the weight of this, we should have the tension in this part of the string. Now, we're making the assumption that the string is close enough to ideal, at least for this part. Obviously, it's not ideal here, but some concessions. We assume that the string is ideal, so in the fact that I don't have to worry about the weight of the string and the fact that the tension of the string is constant. I want to use SI, the SI system, and so the tension in the string should be equal to the weight of what's hanging, which is 0.170 kilograms times 9.8 meters per second squared. And obviously, if this were the lab, I would not be using 9.8.
Using 9.798.
Yep, absolutely. And so what is the tension?
.6657.
Is that what you said?
Yes.
And units? So we have everything except the wavelength. And we just need to figure out what is the vibrating length, and then 2/3 of that is the wavelength. And, ooh, so close to that. Incredible precise measurements here.
I think so.
So I'm just going to, there's a centimeter there. I got this vibrating length is 103 centimeters, or 1.03 meters. So my wavelength is 2/3 of that.
Divided by 1.5,
You wanted a fraction or a decimal?
Decimal.
Okay.
.686 repeating.
The number of the beast. All right. So we can now make our prediction for the frequency. If we get within 5%, there might be tears of joy. Definitely on the inside.
Can we get like, should we give us like a grade or something?
No more times.
I will grade you fairly, how about that?
Okay.
So our frequency, our prediction based upon our results here is we have the square root of our tension, which is 1.6657 newtons, 1.6657 newtons, times my full length, 3.08, I'm sorry, 3.0485 meters. That's not squared. Divided by the mass of that amount of string, which was 3.16 grams or 0.00316 kilograms. And then also on the bottom, we got the wavelength squared, and the wavelength was 0.686 repeating squared.
Alright, gotcha.
And that was meters.
Oh, wait, what the heck? So, 1 point, alright. Oh,
Got 48.399. I don't know if that's right.
I'll back you up on that, hold on.
Right.
I feel like that's pretty close, isn't it?
Eh, we're 20% off.
58
Oh, yeah.
point.
Yeah, I got
Oh.
58.
Yeah, I forgot the square, my bad.
58.
Sorry.
Oh.
Woohoo!
Wait, is that good?
What about that?
58 point what?
284.
384.
Well, I got 284.
What? I got, okay, I don't know what's going on now.
Units,
8.435.
you got 435?
Yeah.
To be
I
hertz.
don't know.
Hertz. All right. Tears of joy on the inside.
How close is that?
The predicted, or the expected result was 60.
Okay, so can we do like a percent error on that? Like,
All right, so our percent error, which value are we gonna take here?
The bottom one.
Bottom one?
435.
yeah.
Let's make it the best.
All right, so, okay, I'll go with that. All right, so the percent error is the difference between the expected value and what we got, which was 58.435, divided by the expected value.
Alright, so 60 minus that big number over, oh wait, no. That blundered. Over 60.
2.6083 repeating percent. And that's why we're the best class in the world.
Yeah, we really
That's
are.
right.
They should all get an A+ for
Is that the closest you've ever had it?
For the crudeness of the experiment, yeah, that is actually really good.
Especially with the air measurement you did with the meter stick.
Yeah, well, I think what helps, because the biggest error I usually see is in the linear density, because I'd already done this beforehand, that I think helped a lot. It's always a question of what length do you pick, because the string is stretched. I mean, the stretch length of the string is different than the non-stretch length. It's not like it's, you know, the non-stretchable synthetics.
That's
Alright.
pretty epic.
Questions to hear?
So the where we got the, I guess, wavelength, the 1.5, that's because it's a third harmonic and we're dividing it in half, right?
That would work here, that doesn't work for every situation, it works for all the two fixed ends.
Okay. So if there were 4, would we do a 2 there?
Yeah. The main reason why, in my mind at least, the 1.5, and this technique would work no matter what, is I know that a full wave does this.
Yep.
And so that's full one there, and then I got a half a one there, so 1.5.
Gotcha, okay, that makes sense.
Yeah, Chance?
Does the length of it not change when it's oscillating? Like, wouldn't that make the string?
That's not the issue you're looking for.
That's-
Yeah, I mean, that is, all the derivations I've ever seen really don't take that into account. They say that the length of the string is pretty much that, so. Part of it is that there is a certain amount of extra stretching that goes on when the string goes in there, so the tension throughout the entire string is no longer the same, because at the point the tension's the highest, their tension is basically what we're predicting right there, and there it's also at the other extreme. I haven't seen any analysis that goes into that level of detail. They all basically what we've done right here. So, yeah, I'm not quite sure how to take that into account, ultimately.
So we need to get our PhD and study that.
I don't think you get a PhD for studying that. This and what we call a physics, close enough.
Close enough.
Once you have your PhD and you've got your professorship, then you can start doing research on this and you can get some publications out of it.
This isn't about like what we're doing during like at all, but I just want to let you know that I have to go at like 2:40 or 2:45 because I have a math test at 3. So, because I forgot to tell you at the beginning of class, so I wanted to tell you right now.
Well, now you've told the entire world.
I can't believe you, man.
Can't believe you're ditching physics for math.
Wow. You gonna leave us here?
I mean, he's done that before. I mean, every time he does it, just a little piece of his grade dies.
Another lab's added.
Years ago, I had doing 251, 252 evening course, and the course right before that for most of the students was physics, for Calc 2 or Calc 3 in the second semester. And so usually their class would end 10 minutes before mine would begin. And so you got a couple of people who weren't taking the math class on time, and then there's this en masse of people from math coming in. Obviously telling me that math is more important than physics. So I don't grudge.
Be a brutal semester for them, dude. Was it like 2-3 hour classes back
Yep.
to back? Straight from Calc 2 to this for 3 hours, yeah. No.
But at least they end the day on physics, which is,
All the better,
Yeah.
set their minds on that.
All right. Other questions before we take a look at the different harmonic? All right. Move this down here. Ordinary plastic tube with ridges. That's the second harmonic.
Is it making that noise?
Third, fourth, fifth. There's a sixth in there. So what we're gonna do is we're gonna make a prediction of what those frequencies are that you just heard, and then we will actually compare it.
Can we go over the science of why it makes that noise? Like,
Magic. All right, so one of the things that's happening here is as it's spinning, this part of the tube is traveling faster than this part. And because it's traveling faster, it's causing a drop in pressure in the air up here than it is down here.
alright,
So since there's less air pressure on this side than this side, air will come sucked up through it.
okay.
Now, the ridges help the air to vibrate. I mean, you can also get the harmonics, if it were a straight tube, it just wouldn't whistle the same way. It'd be more like a, you can hear that with a mask on, and I'm sure they got it. So the ridges get the air to vibrate.
Oh, that's cool.
Ah,
But unlike this, that had two fixed ends, this has two free ends.
I thought your hand was fixed on the one end.
My hand is on one end, but it's still a free end here. In terms of the air vibrating, the question, when you've got a fixed end, you have a node. When you have a free end, you have an antinode. There's nothing to make the air sort of not vibrate here. You're gonna get maximum vibration at this point.
Oh, okay.
Maximum vibration at this point. In other words, when we set up our harmonics here, we have two antinodes. Free end, antinode, fixed end, node.
Does it make any noise if you were to hold it from the center and spin it?
I
Is
think,
that even possible? I don't know. Oh, okay, yeah.
Gotta get like a
Never
baton
mind.
person or whatever.
yeah, I'm trying to think of, yeah, I'm not sure that. You know, what's the sound of one hand clapping? Well, if your hand moves fast enough, it sounds like a regular clap.
One hand clapping. I'm interested to hear that now.
If you were able to move one hand fast enough in order to basically make it sound like one hand clapping, you probably would shatter a couple of them. Yeah, I suspect you burst all the veins in your hand.
That'd be suboptimal.
You really like that word.
All right, so what we're trying to figure out when we want the standing wave is to figure out what is the simplest pattern. That would be the first harmonic. Well, I know it has to have an antinode on each side, so the simplest harmonic, so the first harmonic for two free ends. Harmonic, and that's the simplest pattern. If this distance here is L. How many wavelengths is that?
One.
Half.
Is indeed a half. A full wavelength looks like that. In essence, we chop off the ends. So this is a half a wave. So the wavelength would be 2 times that length right there.